Let's move on to a very important topic of linear systems of equation. And this is important because typically matrices are broadly applicable in solving a set of linear equations. Okay, and what is a set of equation? They essentially have a list of variables and a list of equations that relate those variables. So let's take an example problem and let's see how this might look like. So here I have a set of three equations and I have three variables x, y, z, and this three equation describes the relationship between the variables that I have. Now, if I want to solve this problem and find out the exact values of x, y, and z, which satisfy this three equation together, then we are solving this set of linear equation. And it turns out that matrices are a good way to solve for this problem. So let's see how we can use matrices to solve for this class of problem that we are interested in. Okay. So what we can do here is like these are the set of equations that we have. The variables of interest are x, y, z, right? And what we have is like we have arranging this equation in appropriate manner. And what I mean by that is what we are doing first is all the equations are listed on the left hand side. So anything with respect to the coefficient of the variables x and y and z is on the left hand side of this equation. And then the constant of these equations are on the right hand side of the equality for the set of three equations that we have. Okay. And then all the variables are aligned vertically. So x is aligned with x, x in the first, second, and third. Y, y, y is aligned in the first, second, and third. And z, z, z is aligned in the first, second, and third. So that's another important way that needs to be there. And for those interests where we have no coefficient with respect to one of the variables, we basically 0 times that variable and add zeros wherever that is necessary, right? So once we have this set of those three equations, then they can be written in the form of matrix multiplied by a vector, which we have discussed in the last class. And let's see how we can take this set of equations, three equations, and write them into a form which is a matrix multiplied by vector form. So what I can do is I can take the coefficients of the equations that are there on the left hand side, which is 3, 2, minus 1, 9, 2, 0, 11, 0, 7, and I can use that to create a matrix which is basically listing here. So the first row of the matrix is corresponding to the coefficient of x, y, and z in the first equation. The second row is corresponding to the coefficient of x, y, z in the second equation, and the coefficient of third equation 11, 0, 7 is essentially the third row of this matrix. And then I can multiply this by a vector which is x, y, and z. And that is going to be equal to what we have on the right hand side, which is 5, 3, and 15. Okay. So this is how we have the structured and rewritten the set of equation in the form of matrix multiplied by vector, where the coefficients of the equations are essentially forming the matrix, the variables are forming the first vector, and the constant on the right hand side are forming the second vector, because we know when we multiply a vector by a given matrix, it results in another vector, right? So now let's see how do we go about solving this, right? So this becomes my matrix matrix M, and this becomes my vector x, and that is equal to some constant vector. Let's denote that by vector v. So essentially what equation we have here in terms of matrix vector multiplication, matrix x multiplied by vector x is equal to vector v, where x, M is this matrix, x is this vector, and v is this vector we have listed here. Now what M is, if you recall from our previous lectures, that M matrix, right, multiplying a matrix with a vector is essentially taking a vector and transforming it. So what we are doing, we are taking this vector x and we are multiplying this vector by this matrix M. So this essentially is going to get transformed, and when it gets transformed, that is going to be equal to v. That's the geometric meaning of this set of equations that we have. Now, so by solving mx equal to v, we are identifying the x vector, which after applying the transform M is going to move to vector v. And this is what we need to do. So in order for us to understand what how this is done and how it is carried out, we need to understand this idea of matrix inversion and the geometric meaning of the matrix inversion. So let's take the same example and try to understand some geometric interpretation of what matrix inversion is, because they are required for us to solve for set of equation. Okay. So what I will do, I will take a 2D or simplified example to showcase the intuition behind the geometric intuition behind the matrix inversion. Okay. So let's say we have this set of two equations. Now we can write that in a matrix vector multiplication form. So we did not have a coefficient of x, so that's why we have 0x. So we can rewrite this. Now we can write this equation in the form of matrix multiplies by vector. So the coefficient of the equations, which is two variables, so that's why we have 2 and 2 multiplied by x and y is equal to 2, 5. That's the equation that we need to be having. Okay. Now with respect to this problem, this is the matrix, this is the x, and this is the v vector that we have. Okay. So when we want to solve this problem, right, what we are going to do, let's try to understand the geometric meaning of what this means. So first of all, if I have a vector x, right, wherever that x is, if I multiply that vector by m, what I'm doing, I'm transforming, and this vector will move somewhere. Now this matrix m, which I am transforming, this x has to go to this location 2, 5. Okay. So what essentially I am trying to find, I am trying to find the x which when transformed by this matrix m is going to become this vector v, which is located, whose tip is located at 2 and 5. Okay. So this after transformation has to become, and after transformation the original unit will also get transformed, and in new transformed space the unit vectors are going to be different. Okay. So that's the geometric meaning of the basically multiplying m by x. So we are looking for x which after being transformed by matrix m turns into v. So after multiplication it turns into v. Okay. And this intuition also gives you what the matrix inversion operation is. So what the matrix inversion is performing the transform in a reverse manner, so that if I multiply this vector v by some matrix which let's call m inverse, then this will become x. And that is the geometric meaning of inversion problem. Okay. So when we take that and we basically multiply that by a matrix vector v by a matrix, and it becomes an x, essentially we are doing the matrix inversion. Okay. So this reverse transformation is captured by inverting this matrix, and that is denoted by this symbol where we are taking -1. -1 is essentially inverting the matrix. So if you have matrix m, the inversion is denoted by this notation, m inverse -1, right? This is denoted, and that's what we are denoting. But what it essentially mean is, if I take the right hand side vector and if I multiply that right hand side vector by a inverted matrix of n, I will reach the x vector, and that is the geometric meaning of the matrix inversion process. Okay. So let's see how we can understand that and what it is involved. So if you have this equation mx is equal to v, I can multiply this equation on both hand side, the left hand side and the right hand side, by m inverse, and if I do that, I will arrive at this equation m inverse multiplied by m times x is equal to m inverse v. So we have now a matrix by matrix multiplication is equal to matrix by vector multiplication, and this turns out m inverse m is going to be identity matrix. So this will basically come out, this will become 1 0 1 0 0 1. So this will become eliminated, and we will have this simplified equation which is essentially x is equal to m inverse v. Okay. So let's see how this look like. In the transformed position we have this overall inversion. Okay. So after multiplying that m inverse by m, the transformed I and j is going to become unit vectors. And that's what this m inverse m means, and that always results in this 1 0 0 1 element, depending upon the number of dimensions that are there within the matrices here. So that's the inversion problem. Now, in order for us to compute this matrix numerically, what is the equation that we need to use? And that's an important concept. So let's take the numerical implementation aspect of matrix inversion and proceed with that.